Hello and welcome back. In this lesson we're going to be talking about nuclear fission, nuclear fusion, and the chain reaction that basically drives the energetics of a nuclear weapon. So first let's start off and we're going to talk about fission. And a big question is, why do these things fission in the first place? Well, it has to come down to basically how much energy is, that energy, missing mass, binding energy is present already within these nuclei. They're very big. So adding up all of the constituents, the protons and neutrons in the nucleus, we can come up with something where the binding energy that's holding everything together is not very high. Now, in the case of uranium-235, if we introduce a thermal neutron to this nucleus, so we just add that energy straight up, it has no kinetic energy, and we go ahead and do the calculations on the mass defect, what we're going to find out is that it's approximately 6.5 MeV. Now, if we look at uranium-238 on the other hand, and we do the exact same thing, we end up with a mass defect of only about 4.8 MeV. Now, this actually does make a difference because we're going to have to look at what forces do we need to overcome for a nucleus to split apart. So, looking at what's called the liquid drop model. Now, in the liquid drop model, basically we're taking and we're introducing this energy in the form of the neutron into the center of the nucleus. Well, now it's got this energy, and so one of the ways to look at it is that the energy is going to cause the nucleus to wobble, in effect. And while it's wobbling, so it's forming and deforming and it's stretching around in 3 dimensions, so what ends up happening if you introduce enough energy into the system is that as this plastic deformation of the nucleus is occurring, positive charges get split between one side and another, sort of like a dumbbell shape. Okay, so now they're starting to move farther and farther apart to where they hit that limit of the range of the strong nuclear force, which is the force that holds everything together into the nucleus, and the Coulombic repulsion between the different sets of protons starts to take over. So it stretches, and the Coulomb force pushes it more and more each time it wobbles, till eventually the Coulomb force overcomes the strong nuclear force and boop, splits the nucleus in half. And that's the whole thing behind this liquid drop model. Now, the Coulomb barrier, or the binding energy, it's actually not the Coulomb barrier, it's the nuclear force barrier that's holding everything together. We need a certain amount of energy in order to overcome it. So we need a certain amount of repulsion between those 2 lobes of this deforming nucleus in order to have fission actually occur. Now, if we look at, on this chart, that critical energy, that's how much that you need to overcome with the wobbling. So you need to have at least 7 MeV. For uranium-238, you need that amount of force to push the wobble in order for it to split apart. And for uranium-235, it's a bit lower at 6.5 MeV. Now, again, I showed you some values for the binding energies for both U-235 and U-238. U-238's one is a little bit different, and it has to do more along the lines of it's not an exact calculation. There are a bunch of factors that weren't included, but we'll say for all intents and purposes, good enough. The same with uranium-235. So you have this binding energy and you have this critical energy, which is how much you actually need to push everything across. The binding energy is what you get when you introduce a neutron. So in the case of uranium-238, we just don't get enough energy in order to force this nucleus to split, right? In the case of uranium-235, we get just enough, about 300 keV of extra energy that will overcome the strong nuclear force that's trying to hold everything together so that the Coulombic repulsion just splits it right apart. So that, in essence, is why if you add a thermal neutron to uranium-238, it won't fission, but uranium-235 will. One more thing to consider, though, just like with the mass balance equations we looked at earlier, if that's a negative number, that binding energy minus the critical energy, it means you have to add more energy into the system in order to get it to work. In the case of a neutron, if you shoot a highly energetic, MeV level or above neutron at a 238 nucleus, you will overcome that barrier and it will fission. So U-238 only really fissions with faster neutrons, while U-235 prefers those slow neutrons, but it will in fact also fission with fast neutrons. So if we want to go ahead and write this in terms of the nomenclature that we've been using so far, we have uranium-235 plus a slow neutron ends up producing this compound nucleus, this uranium-236 compound nucleus, which we now know has enough energy to fission, and that's going to result in two basically ejected nuclei. So it's going to split, and those two lobes are going to be themselves become their own nuclei. We'll call it nuclei X and nuclei Y. And then we're going to get some number of neutrons that are ejected as part of this process. So nu is sort of the shorthand notation in the nuclear world for the number of neutrons that are emitted on average per fission. Now these fission fragments, they're not both the same. They're not identical sitting right in the middle of whatever that mass is that has to be divided. What they end up doing is you get a smaller one and a larger one, and that's demonstrated by this graph of the mass distribution of the fission fragments. So we notice that we have two lobes, and so we have sort of right in the middle here. It's between 90 and 95 A, or the mass number, and this lobe right here, it's right around 140, between 135 and 140. So on average, the mass distribution of our two fission fragments are going to wind up somewhere between there. So we're going to have one of the small ones around 90, 95, and we're also going to get one between about 135 and 140, as long as they add up, plus the neutrons that are produced in the particular reaction, to the total number of nucleons that we started with. Now you can get serious outliers, where maybe you're going to get a mass fragment that's all the way down here at about 155. Well, if you're going to do that, it's so massive, it means that we have to, for the smaller one, we have to correspondingly go to the other side, because it, by necessity, has to be much smaller, again, in order to get the nucleon balance to happen. So energy production from fission. Now we've sort of looked at the mass balance. We've looked at how to convert like MeV into other units. So again, we're going to write that very standard equation out, where we have one neutron coming in to U-235. Again, makes that metastable nucleus of uranium-236, which then immediately fissions. And in this particular case, we're going to get a lanthanum nucleus, a bromide nucleus, and two neutrons. Now this is the exact same mass balance that we've done before, and I'm not going to go ahead and write out the math for it, because hopefully you understand how to just plug those numbers in, and what you end up coming up with is about 174 MeV released in this particular fission. Now this is from the fission event itself. So this would be kinetic energy divided amongst the lanthanum nucleus, the bromine nucleus, and those two neutrons as they fly off. But that's not the whole story, because there's more energy that's involved here. It turns out those two fission fragments, they actually are in an excited state. So they're probably going to decay, and they're going to decay either really, really quickly or much sort of further down the road. And so we can split this up into two different categories. One is prompt, and the other is delayed. Now, when we talk about nuclear detonations and what's going on as the weapon explodes, and looking at the output of the weapon, we normally lump the prompt gammas and the prompt neutrons into the energy release for each fission. Now technically they don't come from the fission reaction themselves, but they're produced by radioactive decay of the fission fragments within microseconds of the fission happening. So on the timescales again that we're looking at, it's about the same time. So we go ahead and consider those into the useful energy that's being produced as part of that fission chain reaction. Now later, we're going to get some other stuff where the nuclei are decaying, or for the first time, or undergoing subsequent decays, where we're going to get delayed betas, electrons usually, delayed gammas, generally not delayed neutrons though. And the antineutrino thing on here is just to do the mass balance and the momentum balance of these radioactive decays, but for all intents and purposes, antineutrinos or neutrinos. They don't really interact with anything, so we can really consider their energy not relevant. And the delayed portion to this is usually pushed out to a far enough timeline that it really doesn't affect the nuclear detonation itself. So total energy per fission for uranium-235, again, about 207, although the useful part of that is only about 180. And then plutonium-239, one of the other fissile isotopes, in fact, these are the two isotopes that are used in nuclear weapons, is a bit higher at about 185 on the prompt and 212 overall. Okay, so what we're going to look at here is the energy release when we fission a whole bunch of nuclei at the same time. So imagine that you have yourself a metal piece of uranium-235. Call it 25 kilograms. And you want to know how much energy you're going to get out of that if every single one of those nuclei undergo fission. So first we're going to look at our conversion factors. If we remember, going from MeV to joules, which I don't like to do, calories, which I don't use, kilotons in calories, again, don't use it, or the one that I actually use, which saves a whole lot of time, is the 1 MeV being equal to 3.83 times 10 to the minus 26 kilotons. Now, for this particular example, we're just going to go ahead and assume that all of that energy is useful. So we're going to use that 207. So let's go ahead and take a look at this calculation itself. Okay, so what we're going to do here is we're going to find out how much energy release we get in 25 kilograms of uranium-235, assuming, of course, that every single one of those nuclei undergo fission. So where do we start? Well, we first need to find out how many nuclei is in 25 kilograms of uranium-235. So we're going to start with using our Avogadro's number, and we're going to divide that by the atomic mass of the nuclei in question. In this case, uranium-235. Avogadro's number being 6.022 times 10 to the 23rd. Write this again, 235. Okay, and that is going to be equal to 2.56 times 10 to the 21st. Okay, so now we know how many are in a single gram, but we need to know how many are in 25 kilograms. So we need to multiply this by 1,000 because there are 1,000 grams per kilogram. And we need to further multiply it by 25 because, well, that's how many kilograms we have. So if we do this, what we're going to end up with is the total number of nuclei is going to be 64 times 10 to the 24th in that entire mass of uranium. Okay, so now we know how many that we have. So what's the energy release? Well, we know, or we're going to assume, if we can contain all of the energy in a fission event, and this includes both prompt and delayed, so it's kind of not realistic, we'll say that there are 207 MeVs of energy per fission. Okay? So we have to multiply that by the number of total nuclei that we have. And because we're kind of looking to see, in explosive terms what this ends up being, let's go ahead and use that conversion factor to go from MeV to kilotons, which is 3.83 times 10 to the minus 26. Okay, MeV per kiloton. And so ultimately we end up with a grand total of 509 kilotons of energy release. Okay, so what we saw with that calculation is that we get approximately 509 kiloton energy release from that 25 kilograms of uranium-235. Now, I did a bit of rounding, so it didn't work all that well because the nominal number is about 508 kilotons. But I call it close enough for me not having to do a ridiculous number of multiplicative operations in order to come up with that. And what do I mean by a ridiculous number? Well, let's just take a look at the next slide, where this is the long way to do it. Okay, joules to MeV, calories in joules, kilotons in calories, when all I needed to do was just to go from MeV to kilotons. Yeah, you can do it this way, and you'll get a little bit more precision, depending on how many digits you use. But really, you're not a weapons designer, so I don't expect you to go through all of this every single time you want to find out what a yield is from some mass of a fissile material. So, in contrast to fission reactions, we're going to take a look at fusion reactions. Now, in fission, what we're trying to do is impart enough energy to a nucleus via the absorption of a neutron so that we can get it to wobble and split apart, therefore releasing energy and also our fission fragments and some more neutrons that can then go on and cause further fission reactions, which we'll talk about here very shortly when we talk about chain reactions. Now, in fusion, we need to put energy into the system so that we can get two smaller or lighter nuclei to fuse together, resulting in an energy release. Now, for the most part, when you talk about fusion, you're talking about fusing elements, a very small subsection of elements called the light elements, and these include hydrogen, all of its isotopes, one very specific isotope of helium, which is helium-3, and very possibly lithium. Now, if we go ahead and set up the hydrogen fusion, let's take a look at the two most common reactions that are most energetically favorable, which are deuterium-deuterium fusion and deuterium-tritium fusion. Now, in the case of DD fusion, there are two possible outcomes. One gives you a helium-3 nucleus and a neutron. The other, however, gives you a tritium nucleus and a proton. And they have approximately right around the same amount of energy release. It's a little bit, you get a little bit more energy out of the reaction resulting in a tritium nucleus. Compare that with deuterium-tritium or DT fusion, where you end up getting a huge amount of energy out. You end up with a helium-4 nucleus, a neutron, and 17.6 MeV of energy that's split between them. Now, in both cases, most of the kinetic energy is being carried away by the lightest of the reaction products. In this case, the neutron, or the proton for the tritium reaction from DD. Now, what we really want for producing more neutrons so we can push them into that fission chain reaction we're going to talk about later is you want that first one, but only about half of the time are you actually going to get it. The rest of the time you're going to get tritium. And you may say, oh no, that's bad. Well, not really, because now you're producing more tritium, which can then interact with the deuterium, as we see in the very last one of these reactions, and produce way more energy. So when we're talking about fusion within a nuclear weapon, we're normally talking about deuterium and tritium. And so the tritium is, the deuterium-tritium reaction is kind of the one we want because we have the real high energy neutron coming out. However, deuterium-deuterium reactions are going to happen, and they're either going to produce a neutron, which is going to be useful, or a tritium nucleus, which is also going to be useful because it's going to go ahead and fuse with another deuterium and produce that high energy reaction. Now, unlike fission, the big thing about getting two light nuclei to fuse is overcome that positive repulsion, the Coulomb force between the two nuclei. Now, you can do the calculations using the Coulombic force equation that you saw very early on the charged particle lesson. And if you do that, what you find out is the force required is not so great until you get down to like the distance separating nuclei, or the nuclei diameter distance, if you will. Once you start to hit about that point, the amount of energy required to keep mushing them together until they become a new nucleus ramps up exponentially to where you have thousands and thousands of newtons of force required to keep pushing them together to overcome that repulsion. But that's not really how we end up doing fusion. If that was the case, we could never do it because, I mean, how do you just keep pushing two things that are subatomic together? Well, instead of looking at the force required, we can go ahead and look at the energy required to overcome that repulsive force, that the so-called Coulomb barrier. Now, I have this little diagram here at the bottom. It's also in the lesson notes. And what you'll notice is that the top of the barrier, in this particular case, is right up here about 380 keV, which you would think, I have to give 380 keV into the system the two nuclei want to fuse before this is going to happen. And you would be correct, that's technically how it would work. However, if we look down here, it looks like there's a shortcut through the Coulomb barrier, and this is something called quantum tunneling. It's a completely quantum mechanics related effect. It's probabilistic by nature, it's not guaranteed. So what you'll end up having if you take a look and give these nuclei enough energy to, most of them enough energy to go over the Coulomb barrier, you'll get a certain reaction rate. However, you can give them less energy and still have a very reasonable reaction rate because you're relying on that tunneling effect so that the nuclei require less than the Coulomb barrier energy in order to fuse. That's all this is saying. Now, how do you get that energy to those two reaction products? Well, one, you could take an accelerator and basically shoot them at each other. Although trying to hit, two nuclei, head on, it can be done. We do it, but the engineering challenges on that are pretty impressive. And there's no facility in the world that could do this on a super continuous basis, especially not within something like a bomb, right? There's just not the space for, CERN's Large Hadron Collider. So what we can do is we can say that heat is generally considered the motion of whatever the material is, the atoms or the nuclei inside that material, their kinetic motion moving around randomly is directly correlated to the heat of that material. So if we heat the material up sufficiently so that they have, between them, a couple hundred keV of energy, then just randomly they're going to smash into each other, and we're going to either overcome the Coulomb barrier, or we're going to tunnel through it, and we're going to get fusion. So we don't really need an accelerator, but what we do need are some seriously high temperatures. We're talking temperatures in the range of millions to tens of millions of degrees. And this is by far greater than the temperature even at the core of the sun. Now, I put this little thing on here. Pure fusion is not possible with current technology. And we're going to table that, and then we're going to come back to it when we talk about weapon design and why it's currently unobtainable with current technology. So we do the mass balance. We find out that there's some sort of energy release. Of course, we have to put a lot of energy into the system to get it to occur. But if we want to take a look at what are we actually getting out of a fusion event versus what are we getting out of a fission event, so we'll call it DT versus fissioning of uranium-235. Okay, we can see that we don't get a whole lot of energy out of, say, a system of deuterium and tritium atoms that are fusing. Now, I say all together because that 24.9 includes the energy from both of the DD reactions and the DT reaction. So we're just taking and summing up all three of those energies, and we get 24.9 MeV-ish. So if we look on average, if we have this big hot plasma heated up to millions of degrees of both deuterium and tritium, it's going to average out to something like this. Now in fission, we know we get about 180 MeV of energy out. So it's a lot more, right? Well, let's take a look at the specifics of it, and that is energy released per nucleon. In this case, if you divide the amount of energy released by the number of nucleons involved, you end up with 2.49 MeV per nucleon for fusion compared to a minuscule 0.76 MeV per nucleon with fission. Right? So we're getting more energy per nucleon. That's great, right? That means it's more of an efficient reaction. However, we have way more nucleons inside of a fission reaction, so that is more useful to us. So another way to look at this, instead of energy per nucleon, is energy per unit mass. Now, if we take a look at deuterium-tritium, a kilogram of that mixture, if everything inside of it fused, you'd end up with about 80.5 kilotons, and that's a very large energy release. Now compare that to about 17.5 kiloton release from a kilogram of uranium-235. And you might ask yourself, well, why don't we, use deuterium-tritium, for weapons instead of this uranium? It's obviously much more powerful with a much larger energy release. Well, we have some physical constraints that we're going to have to work against. For one, hydrogen gas, which is effectively deuterium tritium, that's what it is, very not dense. In fact, it's lighter than air, so having these reactions occur in a unit volume means either two things. One, you have a gigantic volume that you now have to heat up into the millions and tens of millions of degrees, or you can somehow compress that gas, that kilogram of gas, into a very, very small volume where that heat can then be applied, and it becomes a little bit more doable that way. But how do you compress, hydrogen gas down to something like uranium densities, 19 grams per cubic centimeter? Well, we're going to talk about that when we talk about weapon design parameters, and then further on when we talk about thermonuclear weapons. So from an engineering standpoint, it's much easier to use uranium to get your energy out than it is to try to fusion two light nuclei. I know this is a bit of an abrupt cut, but after putting the video together, I realized that it was kind of closing in on an hour because I spent a lot of time talking about fission chain reactions. So what I've done is broken this up into two parts. I'm ending the fission fusion discussion here, and then I will have another video right below this one where I'm talking about the fission chain reactions. So instead of having to sit through almost an hour of listening to me blab on endlessly, you can go ahead, watch the first part, take a break, and then come back and watch this section on fission chain reactions.